All right, guys. Good evening, everyone. If you're active, case that you're active. If you're active, indicates that you're active. If you're active, indicates that you are active. We are about to start the class now. If you are active, just indicate that you are active. If you're active, indicate that you are active. Please indicate your presence that you are active. Just indicate that you are active. Indicate. We are starting our class now. Please indicate that you are active. Indicate that you are active. Once you come online, just indicate it in the comment section that you're active. Okay, Joyce. Okay, Uchechi, you're welcome. Okay, Ugochi, you're welcome. All right, so let's keep on waiting for others to join. We're about to start this class tonight. Please just indicate your presence that you are active. Those of you who have already joined, just share the link to your WhatsApp group, please. Share the link to your WhatsApp group. Share the link to your WhatsApp group. Just share. It won't take us anything, just 1 minute. Let us share. Let other people join us, okay? Let's share the link. Good evening, everyone. So please, if you join the group, do us a favor within 1 minute. Just share the link, all right? Share the link, like and comment, so that we can reach out to other students. Okay. All right, so please share the link, share to your departmental WhatsApp groups. Please share. All right. Okay, we're going to start now. Why others will join us later, right? I hope the board is clear from your end, and I hope my voice is audible enough. Okay, so please, once you join us, just make sure you like and comment, then share. Just indicate I'm active. All right, so let's move into circuit analysis, which is a process of calculating the voltage and current in a complex circuit or in a simple circuit. All right, this have to do with Ohm's law. Yesterday we talked about DC circuit, right, where we learned what a DC is, and we say that a DC simply means direct current. It means a circuit that has direct current. And we say that a direct current is a current that flows in one direction. And we talk about the sources of direct current. We talked about the solar cells. We talk about the DC generators. We talk about the batteries, any form of battery either car battery, remote battery, any form of battery possess a DC current. Then we proceeded to what we call the fundamental law of current, right? Current, electricity, where we talk about Ohm's law, and we recall that Ohm's law states that voltage is equals to IR. Now, the current that passes through a conducting wire is proportional to the voltage across its end, right? That increase in current will lead to increase in what? In voltage. This expression is called Ohm's law. This is the mathematical way of expressing Ohm's law, all right? Then we also use Ohm's law to analyze some simple circuits, right? Whereby in which the resistors in such a circuit are connected either in series or in parallel. And we mentioned some important things yesterday. We say that resistors can be connected in series and also in parallel. And I derived the expression for finding the equivalent resistance of resistors connected in series and in parallel. I will say that for resistors in series, this is just a recap. We say the same current, right? The same current flows to resistors in series. The same current flows to resistors in series, and we have different potential difference or different PD or voltage across each resistors connected in what? In series. Then we say that for resistors connected in parallel, we said in parallel we have the same voltage drop, the same PD voltage drop across each resistors in parallel, but we have different what? Different current that flows through each resistors. Now, when current flows from the cell or from the battery for parallel, the current will split. They will split across these different resistors, which will lead to different current flowing through each of the resistors connected in parallel. And we mentioned some fundamental thing to take note of. We say that resistors in series tends to increase the total resistance of a circuit. That for me to increase my total resistance, I have to connect resistors in series. So connection of resistors in series tends to increase total resistance. All right. All of this I'm not going through, but connection of resistors in parallel tends to decrease the total resistance. I'm not going to go through all of this again. I want you guys, for those of you, if today is your first time in tonight's live class, just go through the previous class that was done yesterday. We had a class on this yesterday on Saturday I think that was by 5 p.m. So I'm encouraging every one of you to go through that class. So today's class, we want to look at how to analyze complex circuits. There are some circuits that we cannot actually apply Ohm's law just like that. Are you there? There are some circuits that are complex. What are complex circuits? Complex circuits are circuits that have two independent voltage sources connected in such a circuit, multiple resistors, multiple loops, multiple nodes, multiple junctions. Whenever a circuit have more than one voltage source, such a circuit becomes a complex what? Circuit. In order to analyze the current that flows through each of the elements in such a circuit or each of the resistors in such a circuit, we have to apply a rule, a law called Kirchhoff's what? Kirchhoff's law. So Kirchhoff's law was developed by a scientist called Gustav Kirchhoff. Okay. According to him, he gave two fundamental laws that can be used to calculate the current that flows through a complex circuit and the voltage drop across each of the resistors in a complex what? Circuit. Before we go into Kirchhoff's, I would like to draw a simple circuit that will take note of some fundamental terms. There are some terminologies some terms that we must have to take note of in a complex circuit. These terms will enable us to apply the Kirchhoff's law, both the first law and the second law. We have Kirchhoff's first law and the second law. The first law of Kirchhoff's is called the Kirchhoff's current law, which is called the law of conservation of charges. All right. It's also called the Junction law. The second law is called the Kirchhoff voltage law, which is called the law of conservation of energy. All right. So, but before we go into this law, what does this law state? Before we go into what this law states, or before we start analyzing this law, I want us to look at some terms that we might likely be coming across during the process of analyzing Kirchhoff's. So the first term, please, if you are active, indicate that you are active. If you are following, indicate that you are following. Okay, like I said, we have some terms. The first terms we are going to look at, okay, is called the word junction. The junction. I will draw a circuit to explain what a junction is. Okay, number 2, we have what we call the node. Number 3, we have what we call the branch. Number 4, we have what we call the loop. Number 5, we have what we call the mesh. Okay, let's analyze each of these together. The terms that are used. Suppose we have a circuit, a simple circuit, or let's draw a complex circuit, a circuit like this. Okay, we have 2 battery sources here. We have our first battery source. We have the second battery source. We have our 3 resistors. We have R1, we have R2, and we have what here? R3. Now, why do we say this is a complex circuit? If you look at, we have 2 independent voltage sources. V1 and V2 are 2 different voltage sources. This can be 24 volts. This can be 8 volts. In some case, we can even have another voltage source along this region. We can have more than 2 either. But so far, if you look at what we learned yesterday, we dealt with a circuit that have just a single voltage source. But whenever we have 2 independent voltage sources, multiple resistors, multiple loops like this, multiple branches, definitely this becomes a complex circuit. Either. But the most important things to note, what makes a circuit complex is when we have 2 different voltage sources, okay, or 2 similar voltage sources. But definitely, throughout our Kirchhoff's analysis, we shall be dealing with 2 different or 3 different voltage sources. All right, this can be 24 volts. This can be what, 12 volts. Okay, you must take note that V1 voltage V1 is sometimes not equal to what? V2. Is sometimes not equal to V2. Now let's look at this. Let's define each of these. What is a junction in a circuit? A junction in a circuit is simply a point in that circuit where current enters or leaves the circuit. Is a point in a circuit where current enters and leaves. Are you there? That's called a junction. I'm going to explain this, a junction, using this complex circuit. If you look at this, we know that conventionally, current tends to flow. There's what we call flow of electrons and conventional flow of current in a circuit. Electrons flows from the negative terminal of the cell, while current flow from the positive terminal of the cell. If you look at this cell here, I have a longer part and a shorter part, right? The longer part represents the plus sign, the plus side of the cell. Plus simply means positive terminal of the cell. While the shorter part represents what the negative what terminal of the cell. Current flows from this positive terminal. Electrons flow from here. So throughout our circuit analysis under Kirchhoff, we are referring to, or we are undergoing a study of how much current flows through resistor, not how much electrons. Our emphasis is on current. So current will always flow. Take note, current will always flow conventionally from the positive terminal of the cell. Meaning current flow from this region, right, from this, and enters this resistor. When current enters this resistor R1, the current that flows through this resistor R1 is called what? I1. Don't forget that if I'm to find the current that flows through each of the resistor, let's say for example I1, I have to use my Ohm's law, which is V equals to what? IR. Is that not? Meaning that for I, current becomes what? Yeah? V over what? R. Is that clear? Okay. Okay, so let's move on. But that is not where I'm heading to first. Just take note that current flow, the first lesson, the first thing to take note of is that conventionally, current must flow from the positive terminal of what? Of the cell. From this terminal of the cell. Current does not flow this way. Electrons is what flow this way. Electrons must flow from the negative side of the cell, while current must flow from the other side, which is the positive terminal of the cell. So current flows here. I have a current that flows here, right? Okay. The current can be 2 ampere, can be 3 ampere, can be 4 ampere. So that same current passes through what? I1. If the current that emerges from here is 2 ampere, that means the current that will flow through I1 is still 2 ampere. But one thing you should take note is that the current flows and enters this point here. This is a junction. A junction is a point where current enters and leaves, or is a point where 3 conducting wires or 3 conductors or wires meet. If you look at this, I have 1 conducting wire. I have a wire here. I have another wire. I have a 3rd wire. The point where these 3 wires meet is called a junction. So I can take my junction from here. I equally have a junction here. This is another junction. A point where 3 conducting wires meet is also a junction. This is my junction 2. But looking at this circuit, current is entering junction 1, not junction 2. So when current enters junction 1, that current will continue this way, don't forget, and enter what? R3. The current that flows through R3 becomes what? I3. Look at this side of this cell. What do we notice here? Current will flow. This side of the cell is negative, right? While this side is what? Positive. That means current will flow this way. Conventionally, current will flow this way. So the current that emerges from this cell that passes through R2 will be what? I2. Don't forget. Any current that flows through a resistor takes the name of the resistor. If the resistor is R1, current will be what? I1. If the resistor is R2, current must be what? I2. If the resistor is R3, the current that flows is what? R3. What do we notice here? I1 enters the junction. I2 also enters the junction. Then I3 leaves the junction. So a point where current enters and leaves a junction. So a point where current enters and leaves is called a junction. It's called what? A junction. This is where Kirchhoff's first law emerges from. The Kirchhoff's first law is called the law of junction. The law of junction says that, or Kirchhoff's current law, which is also regarded as Kirchhoff's first law. Kirchhoff's first law is called the junction law. The junction law is also called the law of conservation. Conservation of charge. It is also called KCL, Kirchhoff current law. In some material, they also call it the nodal law. the nodal law. Okay, but the most important one we use is either we use junction law or KCL, or we use law of conservation of a charge. The law says that the total current rather, entering through a junction in a given complex circuit must be equal to the total current that leaves that same junction. The total current that enters a given junction must be equal to the total current that leaves. Meaning that for this junction law, we are saying that total current that enters, right, that enters a given junction must be equal to total current that leaves the junction. If you look at this diagram here, I1 and I2 are entering the junction. So I have here I1 plus I2 is the sum. These two currents are the sum of all currents that we enter junction 1. Is equal to the total current that must leave. I3 is the current that is leaving, meaning I1 plus I2 is equal to what? I3. This is what Kirchhoff's first law is saying, that in a given complex circuit where current flows, that the total current that enters through a particular junction must be equal to the total current that leaves, okay, that same junction. But the most important thing I want us to take note is that junction is a point where currents enters and leave, or a point where more than 3 conducting wire meets, which is this. So I have junction 1, I have junction 2. The next thing I want us to take note is called the node. I want to quickly rush this so we can go into the main business of the day. A node is a point where 2 conducting wire meet. I have a node here. I have a node. Let's call it A, call it point B. Let's call it point C, call it point D. Let's call it point E, and here what? Point F. I have a node, I have a node, I have a node here as well. A point where 2 wires meet. 2 wires are meeting here. I have 1 wire, I have another wire. This is a node. I have 1 wire, I have another wire. This is also a node. I have 1 wire, I have another wire. This is also a node. Then on this side, I have a node here. I have a wire here, and that wire here, or a conductor and that conductor. This is a node, node E. I have node F, a conducting wire, a conducting wire. I have a conducting wire, a conducting wire, a conducting wire, a conducting wire. This is also a node. But the main definition of these 2 points is what? Junction. Because current is entering and leaving at the same time. The next thing I want us to take note is called a branch. A branch is a space between 2 nodes that contains some elements. Like we have this. I have a branch here from point A to C is a branch. All right. A branch is like a line that separates 2 nodes. But in a branch, there must be some elements. Those elements can either be what? A resistor or a battery source. So this is a good branch. This and that branch. This is a branch. This is a branch. This is a branch. This and this are not regarded as a branch because we don't have any elements across B, D, and D, F. The only parts we have elements is A, B. What's the element here is a battery. What's the element here is a resistor R1. What's the element here? R2. What's the element here? Cell V2. What's the element here? R3. So I have how many branches? Let's see. I have 1 branch, 2 branch, 3 branch, 4 branch, and 5 branch. All right. So that's a branch. Then a loop. A loop is simply your choosing direction of current. You're choosing direction of current. That is called a loop. A loop is your choosing direction of current. That is called a loop. Let me explain this. There are 2 kinds of current you must have to take note of. Number 1 current, I've already mentioned, is a conventional current. Conventional flow of current. Conventional current. That's the first current you must take note of. Number 2 current is called the assumed current. This is the assumed current. The current you are assuming is called the number 2. This is also regarded as loop current. Loop current. Loop current. Okay? This is our loop current. Okay. All right, the assumed current sometimes gives the actual direction of current. It gives the actual, sometimes it gives, but sometimes it does not give. But if it does not give, does not mean the value of your current is not correct. Okay? Does not mean it is not correct. Are you there? So whenever we are taking our loop, we have two loops here. We have our loop 1, this loop A, and this what? Loop B. Okay, we can take our loop this way, meaning our assumed current is flowing clockwise. This region, this direction means what? Clockwise, right? Clockwise, like the direction of a hand of clock. This means clockwise. This direction means what? Anti-clockwise. I can decide to take my loop clockwise or anti-clockwise. I can decide to take my other loop here to be in anti-clockwise, or I can either use clockwise, anti-clockwise, clockwise. Any of these you are taking will still give you the same value of current. We have a lot to discuss here, a lot to discuss. So I'm going to make sure that I exhaust everything tonight. And at the end of the day, I will drop an assignment in the comment section for you guys to practice. All right? Or if you are not in our WhatsApp group, make sure you join the WhatsApp group for the assignment. 961. This is my WhatsApp number. DM me, then I will add you to the WhatsApp platform where the questions will be sent for further study. Okay. Now that is a loop. Then a mesh is just like a loop. A mesh and a loop are just the same, but the mesh is a loop that has no other loop inside. A mesh is the smallest part of a loop, or we can say a mesh is a loop that has no other loop inside. That's called a loop. I won't go into this. Let us continue with Kirchhoff's. Please, if you are following, indicate in the comment section that you are following. Please indicate that you are following in the comment section. Indicate that you are following. Okay, so I want us to finish up this. Look at that. Now let's go into now we now understand some of the terms, right? We use in a circuit. We understand the terms we use in a circuit. This A, this B. Okay. Some of the terms we are using in the circuit. We have analyzed that. Now let's look at Kirchhoff's law. The first law is called the Kirchhoff's current law. The Kirchhoff current law. This law is also called the law of conservation. The law of conservation of charges, or is also called the junction law. The junction law. Okay, the junction law. What was the law saying? The law is saying that if you are given a complex circuit or in a mixed circuit like this, that the sum of all current entering a particular junction in the complex circuit is equal to the sum of all current leaving the circuit. Or the law can also be said to be that the sum of all currents in a complex circuit, the sum of all currents in a complex circuit, both the ones entering and leaving, is equals to 0. The sum of all current in a complex circuit is equals to 0. So what the law is saying here is that the sum of all currents is equals to 0. But let me mention the first one that says the sum of all current, right? The sum of all current entering a circuit in is equal to the sum of all current outside, out of the circuit. The sum of all current entering a given junction in a circuit is equal to the sum of all currents leaving that junction in a circuit. That is called the Kirchhoff first law. The sum of all currents entering a junction in a complex circuit must be equal to the sum of all currents leaving that same junction in that complex circuit, or the algebraic sum of all the currents is equal to what? 0. Let me explain this. Let's look at this. We have seen that current I1 and current I2 are entering this given junction. So the sum of current entering this given junction for this diagram is simply I1 plus what? plus I2. The sum of all currents that enters is this. Then the sum of all current leaving, I2 is leaving the junction, is passing through a root 3. So this will give us equals to what here? I3. Now the second one says the algebraic sum of all the currents in a complex circuit must be equals to 0. What does that mean is that when you move this I3 across this side, that will give us I1 plus I2 minus I3 is equals to what? 0. This statement simply means sum of all current equals to what? Somebody? 0. So there are two ways we can state Kirchhoff current law or Kirchhoff conservation of what? Charges. All right, which is called the junction law, is that in a given complex circuit, the sum of all current entering the junction of such a circuit is equal to the sum of all current leaving the junction, or the sum of all currents in such a complex circuit must be equal to 0. Okay, that is Kirchhoff's first law. Let's look at this. If I have a system of currents, I have a junction here. I have my current I1. I have another current here. Let's say I have I2. I have 3 branches. I have branch I3. I have branch I5. I have branch I4. And we want to apply Kirchhoff's first law. Okay, the first law says the sum of all current entering, I1 and I2 are entering this junction. I3, I5, and I4 are leaving. So the sum of all current entering the junction is equal to the sum of all current leaving the junction, right? Leaving the junction. So entering the junction, we only have 2 currents, which are what? I1 plus what? Plus I2 equals to what? I3 plus what? I4 plus what? I5. That is Kirchhoff's first law. Or we can bring the whole of this current to this side. That will give us I1 plus I2 minus I3 minus I4 minus I5 equals to 0. So sum of all current in a complex circuit is equals to 0. This is Kirchhoff's first law. Let's see a given question. If we are given that current I1 equals to 2 ampere and current I2 equals to 4 ampere are entering, they are entering a junction. They are entering a junction, and current I3 equals to 3 ampere and current I4 equals to unknown. Okay, and current I4 are leaving the junction. Then the question says find I4. Find I4. This is very simple. This is very simple. To find I4, the sum of all currents entering the junction equals the sum of all currents leaving the junction, right? Entering the junction, I1 and I2 are entering. I1 plus I2 equals to I3 and I4 are leaving. So I will say it equals to I3 plus I4. Or the question said find I4. So what's our I1? We have 2 plus what's our I2? I2 is 4 equals to our I3 is 3 plus I4, right? Okay, so 2 plus 4 is 6 equals to 3 plus I4. That means our I4 becomes what here? 6 minus 3. So I4 will give us 3 ampere. So the value of I4 that is leaving the junction with that of I3, the value is what? Is definitely 3 ampere. All right, okay. Now let's look at Kirchhoff's second law. Please, if you are following, indicate in the comment section that you are following. Indicate in the comment section that you are following. Let's look at the second law. Kirchhoff's second law. Now, before we look at Kirchhoff's second law, I want us to see what really happened in a circuit, in a complex circuit. I want us to see what really happened in a complex circuit, like we just saw. Okay, if we have a complex circuit, where we have a cell, we have a resistor, right? R1, we have a resistor R2, we have resistor R3, and we have our second cell. Please, guys, take notes. Pay attention to this part. This is where I want to bring in the major secret behind Kirchhoff's. All right? The major secret behind Kirchhoff's lies in what I want to say now. So every one of you must have to pay attention. All right? Okay. So sorry for that little break. I just needed to fix one or two things. Now, this is a complex circuit. I want you guys to please pay attention. This is where the secret behind Kirchhoff's lies. We have seen the first law, and I believe it's well understood. Please, if you know you understand the first law, indicate that in the comment section. Please indicate that in the comment section. If you know you understand the first law, indicate that in the comment section. If you know the first law is clear, indicate that in the comment section. Please indicate that in the comment section if it is clear. Now, let's look at the main circuit analysis. Is that current flows, conventionally, real current. When I say real current, we are talking about conventional current. Real current will always flow from the positive terminal of the cell. Real current flows this way. Right? We agree. Okay. It flows this way. Sorry. Real current flows this way. Right? It flows this way. From the plus side of the cell. This is the plus side. The longest side is a side that carries the positive terminal. Is that not? So current tends to flow this way. Now listen. The job of the resistor is to resist the flow of current. When current is coming, when this current you are seeing here, is coming through the resistor. The resistor will oppose the flow of current, which will make the current to drop from high potential to a low potential. Yeah, there's a change in PD here. All right, current move from high voltage to a lower voltage to a resistor. So at this point, we have a higher voltage. Here becomes a lower voltage. Whenever current flows through a resistor, there is a drop in voltage from positive toward negative. Positive means high voltage, high PD. Negative means what? A drop or a fall or a lower voltage. Reason because current is flowing in this direction. How do I know? This side is positive. When current comes, it carries that positive charge, deposited it here, and when the current flows through here becomes negative. Meaning that if this cell, let's say if this cell is somewhere here, if the current is flowing to this direction, here becomes positive, it becomes negative. So what I mean is this. Let's say I have a resistor here, and I have a cell. This is the positive side of the cell. This is the negative side of the cell. Current flows this way, right? When current flows this way, here becomes positive, it becomes negative. But if, peradventure, let's say we have a resistor and the cell is placed somewhere here, all right? It's placed somewhere here, okay? What do you notice? Current will flow this way, right? Here becomes positive. Let me adjust this a little. Here becomes negative and positive. So we have here as positive and here as what? Negative. Because current tends to flow from a higher voltage to a lower voltage to a resistor. So when current is coming, this side of the cell of the resistor becomes what? Positive. Here becomes what here? Negative. The same current is flowing down, right? If this current I3 move through this arrow tray, it will come to make it be positive. It becomes what? Negative. Meaning that across my arrow tree, as current is going down, there will be a drop in potential difference in PD from plus to what? Minus. Current must flow from higher voltage to a lower what? Voltage. So as current is coming with a higher voltage, which is this plus. Once it crosses through the resistor, it will drop to a lower voltage, which is minus. Then along this region here, this current is flowing upward, right? Here I have my I2 here. As this current is coming this way, where do you think the minus sign will be? And where do you think the plus sign will be? Definitely, the plus sign will be here. Here will be what? Minus. So current will flow from the positive side of the what? Of the cell. Deposit what here? Positive, meaning it's coming from a higher voltage, positive, to a lower voltage. Then across here we have positive, negative. Here we have positive, negative. Let me ask a question. What if we have a resistor here and that resistor here? What do you think will happen here is that, let's call it resistor R4. What will happen? Current is still flowing down, right? It's flowing down. It's coming down this way. So the current here is definitely what? I3. Will be I4 rather. Will be I4 because I have resistor 4. So where would you think we are going to experience a drop and a rise? There will be a drop here by minus. There will be a rise here by plus because current is flowing. Positive sign means there is a rise in PD. Negative means there is a drop in PD. Whenever current flows through a resistor, there will be a loss of energy. That loss of energy will lead to a drop in PD. That drop in PD is what we are seeing as negative. Am I communicating? There must be a drop in PD because energy has been lost through work done. Don't forget that V is always equals to work done over charge. Work done over charge. As current flows, whenever work is done, there must be a loss, a drop in what? In PD. Whenever work is done, there will be a loss of energy. That loss of energy will lead to a drop in PD. So as current is flowing through the resistor, there will be a drop along the resistor. But what happened? What if the current is flowing this way? What if current is flowing this way? That means the reverse becomes the case. Here becomes positive. Here becomes what? Negative. What if the current is flowing upward? Here becomes upward. Here becomes positive. Here becomes negative. Here becomes positive. Here becomes negative. Is that clear? If this explanation is clear about voltage drop, and voltage rise, please let me know in the comment section. If you know that what I just explained is clear, please indicate in the comment section, because I want to talk about the Kirchhoff second law, which is the law of voltage, Kirchhoff voltage law. Please, if this is clear, indicate in the comment section. Please, if it is clear, indicate in the comment section. Please indicate in the comment section. Please indicate in the comment section. Now let's move. What does the second law actually say? The second law is called the Kirchhoff voltage law. The law is saying that the algebraic sum of all PD in each of these elements is equal to 0. The algebraic sum of all PD, potential difference, in a complex circuit must be equal to 0. The algebraic sum, meaning the sum of all voltage, is equal to what? 0. Sum of all voltage. If I'm to add my voltage here, plus my voltage here, plus my voltage here, plus my voltage here, must be equal to 0. What that means is that since my loop is this way, our loop, this is our assumed. Don't forget that we say we have two ways of representing current. The first one is called the real flow of current, which we refer to as conventional flow of current. Number two is what we call the assumed, which is your loop current, your loop. Here we have our loop showing clockwise movement. I mean, here it shows what anti-clockwise what movement. What does this law is saying? If I'm to consider loop A is simply A, B, C, and D. This is my loop A. Loop B is simply C, D, E, and F. That's my loop B. So let's consider loop A and see what we're going to generate from here. The law is saying that since our loop is going clockwise, meaning the potential difference here is the rise from negative to positive. Here will be plus V minus. Why do we say minus? Because when we move along this resistor, there's a drop in PD. The drop in PD here, PD is V is equals to what? IR, right? The drop in PD will be what? Minus I1 R1. There will also be a drop in PD here, which will be minus I3 R3. There will also be a drop in PD here, which will be minus I4 R4. PD is simply IR, right? That is our voltage, is IR. What do we say here is plus? The PD here is actually IR, is plus IR. Why is it plus IR? Because the loop is showing movement from negative terminal towards positive or terminal. So there will be a voltage rise. According to the loop, there's a voltage rise here, which is what? Plus IR. Then along R1, there will be a voltage drop because the loop is showing clockwise. So I'm moving this way. I'm going this way. I'm looking at the loop direction, not the conventional flow. The conventional flow has done its own job by telling us what is the value of the sign here. That this sign here is positive, here is minus. Yeah, here is plus, here is minus. The job of the real current is to tell us where to place our potential rise and what and potential what drop, which we have already done. Plus, minus, plus, minus, plus, minus. Then I will now use my loop to get the equation that will be needed to solve for the current that flows through each of the resistors. And I'm saying that since we are moving clockwise, clockwise means this way. So when we get to this cell, there's a rise in PD from minus to plus. Clockwise means I'm going towards what? Positive terminal of the cell. Then this way, loop is also showing a drop, meaning from plus to minus. So my PD drop here is what? Minus I1 R1. Then along this region, our PD in R2, R3 is I3 R3. But it will be minus I3 R3 because there's a drop, right? As the loop is going, it's showing that there's a drop. Yeah, we also have a drop in PD. But the PD in R4 is actually I4 R4. Why do we assign negative? It's simply because of our fall. There's a drop, a fall in what? In PD from plus to what? To minus. Then if I'm to consider this loop, this other loop here, this is our loop C, D, E, and F. Let's look at loop C, D, E, and F. The loop is going this way. So if I'm to go anti-clockwise or counterclockwise, right? It means there will be a rise in PD from minus to plus. Is that not? But along this region, what do you notice? There will be a fall in PD. The PD here will be I2 R2, right? The PD here, I've already analyzed the PD in R3, which is what? Which is I3, R3. The PD is for I4, R4. So here we have a rise in PD in this cell. We have a fall in PD, which is minus I2, R2. Here we have another fall in PD because I'm going this way, right? Good. Then here we have another fall. Since it's going this way, it will take us from plus to minus for R4. So there's a fall here. There's also a fall here. But what if we assume both clockwise? Let's see what this will give us. For this clockwise, so my PD will be what here? Minus. I'm going this way, minus. My PD will be what here? In this loop now, loop C, E, D, F. I'm not talking about this loop. I'm talking about this loop here, loop B. So here will be positive what? Okay, negative what here? There will be a drop in PD here. Here we have a rise because I'm going in a clockwise direction from minus to plus, a rise in PD. Here we have a rise in PD. Now, instead of having minus I4, R4 in this loop, I will now have plus I4, R4 because my loop is showing what? Clockwise, meaning from minus to plus. Here, from minus to plus, there's a rise here. Also, along R2, there will also be a rise, which is from minus to plus. Let me give us a simple circuit to explain this second law. I know this is a major part. I will dwell more on this until every one of you understands it. If I have a simple circuit like this, okay, let me just come this way. Here we have 5 ohms. Here we have 10 volts. 10 volts. The voltage of the battery is 10 volts. And we want to verify. We don't say verify Kirchhoff voltage law. Let's verify Kirchhoff voltage law. The first thing, like I said, is determine your flow of real current. The flow of real current must have to move this way, right? Real current must have to move this way because this part of the cell is negative. Yes, positive. I will say current tends to flow from the positive terminal of the cell. So current flows this way. Is that not? Let's call this resistor R1. Let's call it R1. So when this current enters here, it enters as I1, right? It enters as I1 because I have my resistor 1. This is my R1. Now, if I'm to choose the loop this way, to choose a loop in my, let's say I'm choosing a clockwise loop, right? This is a clockwise what? Loop. I will use both clockwise and anti-clockwise to verify KVL. I will see that the result will be the same thing. Now, the first thing we need to do is that recall, or we are given from the circuit that our voltage is what? Is 10 volts, right? Our resistor is 5 ohms. Then let's find the current that flows through this circuit. Now the first thing. From Ohm's law, right? From Ohm's law says that V is equals to what? IR. So from here we can say that our current is equals to V over R. By the time we divide both sides by resistor, that will give us current equals to V over R, right? That will give us our V is actually 10 divided by our resistor is 5. This will give us what here? 2 ampere. That means the amount of current that is flowing through this circuit is actually 2 ampere. So that means 2 ampere of current is flowing. 2 amp of current is flowing. That means my I1 is equals to what? 2 amp, right? Good. Equals to 2 amp. Now let's verify Kirchhoff voltage law. The law is saying that the sum of all voltage must be equals to 0. Our loop, this is my loop. The loop here is going in a clockwise direction. So the first thing we need to do is to indicate our signs along the resistance, right? Already, since the flow of current is in this pattern, in this direction, as current flows down, here becomes positive, here becomes what? Negative. So along this, my loop is going this way. It means from negative to positive. Is that not somebody? So the sum of all PD, the PD here is actually 10 volts. So let's find the PD here along this region. So what we do here, let's sum up the voltage in this cell plus the voltage in this cell. The voltage in this cell is plus 10. Why is it plus 10? Because there's a rise in PD from negative to what? Positive. If the loop is going this way, anti-clockwise, it means I will use minus because it's showing from positive to what? Negative. Since I'm assuming my current to move in a clockwise direction, that means my voltage, there will be a voltage rise from negative to what? Positive. So along this region, what we notice, the current is flowing. There is a fall of PD. Current flows from higher voltage to what? A lower voltage. Since my loop is in the same direction of the flow of current across the resistor, it means I will have what? Minus I1 R1, because the potential difference, our voltage across R1, voltage across R1 is actually I1 R1, which is equals to what? V1. From V equals to IR. So the voltage here becomes I1 R1. Are you there? So let's verify and see. So that will give us plus 10 minus our I1 is 2 ampere times our R1 is 5. So 2 times 5. So here we have 10 minus 2 times 5 is 10. The answer remains 0. Are you saying that we have verified Kirchhoff voltage law that says that the sum of all voltage must be equals to what? 0? That is verification. That means Kirchhoff law, second law, holds. Now, what if we are taking our loop in this direction? What if the loop is in this direction? What if the loop is in this direction? This is our loop in this direction. So what do we notice here is that current is still flowing this way. The signs will not change. The value of your sign is determined by the direction of the conventional flow of currents. It will not change. Here remains positive, here remains negative. But you can change your assumed current. Your assumed current is your loop. In this case, I'm changing my assumed. I'm assuming that the flow of current is this way. We have seen the first loop, the first direction, which is what? Clockwise. And we got to want to verify. What if I decided to choose a different route altogether? And we now considered a counter-clockwise direction. Let's see what will happen here. Second law is still saying that the sum of all voltage must be equals to 0. What we notice here, along here, because my loop is in anti-clockwise direction, okay, it means there will be a voltage drop here, which is minus 10. The voltage drop here is minor because the loop is moving from positive to negative. So here we have minus 10 volts this way. This way. Is that clear? Now, when we continue movement, the movement of the assumed current, there will be a voltage rise from negative to what? To positive. Is that clear? So what will be here? Plus I1 R1. Don't forget that the voltage across this resistor R1 is I1 R1. But because the loop is showing, is moving from negative to positive, here becomes positive I1 R1. Note that anytime the direction of your loop is opposite to the flow of current to a given resistor, we must have to take the potential difference as positive. It must be positive. From what I just showed you here, why I don't want to give us some things to come is that from your sign, you can determine the signs that if my loop is taken in this direction, meaning it is moving from negative to positive, then we have plus. But if I'm coming this way, it means from plus to minus. Here will be minus, then the value of my voltage will be what? Be plus, because I'm going this way. I'm going in the clockwise direction. So clockwise direction and that of counterclockwise direction will not give us the same sign, but we must have the same what? The same result. Are you there? So from here we have minus 10 plus I1 is 2 ampere, R1 is 5. That will give us minus 10 plus 10. The answer remains was 0. So Kirchhoff voltage law is verified. Please, if you are following, indicate in the comment section. If we are following, indicate in the comment section. Let's see another circuit. Let's look at another circuit. Let's say if I have a circuit like this, and here we have 24 volts, and I have a resistor. I have another resistor. Okay. I have R1, I have here as R2. I want to verify Kirchhoff's second law. Here I'm not solving for current that flows through a resistor. If I'm to find the current that flows through a resistor, we know what to do. We have to find our R equivalent, then divide our voltage by the value of R. That will give us the current that flows through. Although I'll pass through that process, but here we want to verify. Let's verify. Let's verify KVL. Let's see. KVL says sum of all voltage is equals to what? 0. Now I want to choose my loop. I'm choosing this direction. All right. Current is flowing from this part of the cell is the negative part. Here becomes what? The positive part of the cell. So that means current flows in this direction. Current that enters R1 is I1. The same current we enter, right, and continue, also enters what? R2. All right, as what? As I2. Now the next is to determine where we experience a rise and a fall in each of these resistors. Here we experience a rise here. Here we experience what? Here? A fall. Because current must flow from higher voltage to a lower voltage. Plus means higher voltage. Minus means lower voltage. Then along this region, here becomes plus, it becomes what? Minus. But don't forget that the voltage here is I2, R2. While the voltage here is I1, R1. Yesterday we learned that whenever resistors are connected in series, the same current flows through them. So R1 and R2 are in series. So the same amount of current that flows through R1 will flows through R2. The same current that emerges from this cell must have to flow through R1 and R2. So before we solve, just note that I equals to what? Yeah, I1 equals to what? I2. Now the next thing we have to find is to find our R equivalent, right? Good. R equivalent here will give us R1 plus what? R2, because R1 and R2 are in series. We learned this yesterday, so I won't go deep into this. So my R equivalent becomes the sum of these two resistors. Okay, we don't have a value. Let's assume that R1, if R1 is 2 ohms and R2 is 4 ohms. We are assuming a value because I want to verify Ohm's law. Any value we choose there, we still get the same answer. Okay, why verifying? So let's sum up this. We have 2 plus 4. This will give us here, our R equivalent will give us 8 and 6 what? 6 ohms, right? Our R1 is 2, R2 is 4. Then we have here as 6 ohms. But recall that V is equals to what here? IR. So let's find the total current that flows through this circuit. That will give us I equals to V over R. R what? Equivalent. So to find the current that flows through this circuit, we have to divide the voltage by what? By our R equivalent. Okay, so let's proceed here. So we have here to be I equals to, our voltage is 24 divided by 6. So when we divide that, that will give us about 4. So we have 4 ampere. So that means the current that flows from this battery is 4 ampere. That same current enters arrow 1 as 4 ampere. The same current enters what? Arrow 2 as what? 4 ampere. Are you there? Because arrow 1 and arrow 2 are in series. And we say whenever resistors are connected in series, the same current that flows through the first resistor must also flows through the second resistor. Don't forget. So that means that our total current is equals to I1 equals to what? I2 equals to 4 ampere. Are you there? So we have gotten that. But what to verify? Let's verify Kirchhoff's. Let's verify Kirchhoff that says the sum of all voltage is equal to what? 0. The sum of all voltage is equals to 0. Now, what do we notice here? Our loop is going in a clockwise direction. Meaning I'm moving from a lower voltage to a higher voltage. The loop is this way. Yeah, from higher to what? Lower. From higher to lower. Since I am moving from lower to higher, it means that my voltage here will be a voltage rise. And what's our voltage rise? Plus 24 volts. Plus 24 volts. When we move again, the loop is showing clockwise. So when we move this way, if the assumed current is taking this way, it means we are moving from positive toward negative. There must be a voltage drop as what? Minus I1 arrow 1. The voltage across arrow 1 is I1 arrow 1. But because there is a drop according to the loop direction, I will use what? A minus. Then on this side, there's also a drop, which is what? Minus what? I2 arrow 2. So let's analyze and see. Then we have 24 minus I1, I2, I, and I. They are the same because they are in series. So we have here as 4 times our arrow 1. Our arrow 1 is 2, right? Minus I2 is also 4 times arrow 2. Arrow 2 is 4. So we have here as 24 minus 4 times 2 is 8, okay? That is 8 plus 4 times 4 is 16. What do you notice here? We have 24 minus 8 plus 16 is 24. When you subtract these two, what we have here? 0. That means KVL is what? Is verified. Is verified. We have verified KVL, Kirchhoff voltage law. Someone else might likely want to ask, sir, what if we take our loop in this direction? Will I have the same answer? If I'm going in this direction, will I have the same answer? Of course, yes. You should and you must have the same answer. Let's see if we're going to have the same answer. If my loop is taken in this direction, so let's move. It means along the cell, there must be a drop because the loop is going this way. Don't forget that never you touch the flow of current. This remains positive, this remains negative. The loop is what will tell us what will be the sign of the equations, like we just saw, right? That is a loop. Now, the loop is going from plus to minus, meaning minus 24. I'm done with this part. Minus. From here, I'm going this way, minus. Unlike the first, which is plus, right? Okay. The voltage here will be a voltage rise because the loop is showing from negative to positive. So we have plus I2, R2. Along this region, the loop is moving from negative toward positive. So we have plus I1, R1. So we have minus 24 plus our I2 is still 4. 4 times R2 is 4 ohms plus I2 is 4 times 2. This will give us minus 24 plus 16 plus 8. The answer is still 0. So anyhow you want to take your loop, the sum of all voltage must be equal to 0. Now we have seen Kirchhoff's first law, Kirchhoff's second law. Don't forget the first law says that the total current that enters a junction in a complex circuit must be equal to the sum of all current that must leave that same junction. All right. And we see the second law says that the sum of all voltage, right, in a complex circuit must be equal to 0, or the algebraic sum of all voltage must be equal to 0. Now let's solve some problem. Now we have learned. Let's now solve some problem. Let's now solve some problem. Now we have learned. Let's now solve some problem. All right. Let's solve some problems. Please, if you are following, indicate in the comment section. If you are following, indicate in the comment section. Please, if you just join us, make sure you start the video from beginning. You can always watch the video from beginning for proper understanding. All right. Okay, let's start. I have a question here. Let's do a circuit. Let's do a circuit. 24 volts cell. The battery here is 24. And we have our resistor. R1, we have a junction, we have another resistor, then we have another resistor, (24 volts). Here our R1 is 3 ohms. Here we have our R2, 4 ohms. We have our R3, which is 12 ohms. It's 12 ohms. All right, so we're asked to find the current that flows through the resistor, current that flows to each resistor. All right, so let's solve this. Let me bring this in. This is my R3, which is equal to 12. And let me say 12 ohms. This is our R3. Okay, look at this circuit. This is a very simple circuit. But the question requested that we should use Kirchhoff to solve this. I can use the normal circuit analysis, the simple one we learned yesterday. I can just resolve these two, right, in parallel. Then their combination will not be in series with this. Is that not? But I want to see how we can use Kirchhoff's law to solve this problem. Kirchhoff's law to solve this problem. Now, take note of this, is that we have just one cell. This is the cell here, right? The battery. Is that not? Current tends to flow this way, right? The current that flows through R1 is what? Is I1. This current continues, but the current that flows through R1 flows from higher voltage, right, to a lower what voltage. Is that not? When that current gets to this point, this is my junction. I have junction, first junction. I have another junction, right? When current gets to this junction, what do you think will happen? There will be a splitting. Why do we have a split? Is because these two are in parallel. The current that flows through R2 is not the same current that flows through what R3. Because we say that in parallel connection, different current flows through. The currents we have to split into 2 or 3, right? Then the first current will enter here, second will enter here. Let's see. So there's a current that flows through this region, right? That current is called what? It's called I2. Across resistor 2, it's called I2. This same current here, once it gets to this junction, it will split here, also split here, right? Also move to this direction. The current that flows through R3 is actually what? I3. So I have my I3 across R3. I have my I2 across what? I2. I have my I1 across what? R1. But let's look at this. There will be a drop, right? A drop. I2 flows from higher voltage to lower voltage. So here becomes plus and what? Minus. What about this side here? It becomes plus and what? Minus. So what do we do after this? This is my I1. I have to take my loop. Let me assume my loop is clockwise in both. Now we have seen that any direction you are taking for your loop will still give you the same answer. So don't be confused if someone is using clockwise and you are wondering why they're using anti-clockwise, or can I use anti-clockwise? Can I use clockwise? Which one is convenient? All of them are the same. Whether you use clockwise or anti-clockwise, you must get the same answer. Are you there? So I hope you guys are following. Okay, so let's move. So looking at this now, let's consider this loop. I have loop A and what? Loop B. So let's consider. I will just say analyzing loop what? Loop A. What is loop A? Let's put some alphabets across each of this node. I have node A, node B, node C, node D, node E, and what? Node F. These are my nodes, right? These are my nodes. These are my nodes. These are my nodes. Either. So loop A is A, D, C, and what? And B. Okay? A, D, C, and B. Or we can start from here, B, A, D, and C. This region is just the node apart from this side. That is my loop A. This region is just the loop A apart from this side. So all of these are my loop A. Then for loop B, this is also part of loop B. Don't forget, this is a part of loop B. This loop B, this loop B, this loop B. Now let's look at this. Analyzing loop A. For the first law, the first law is saying that the sum of all current, right? Okay, I will have started with the first law before analyzing loop A. Sorry. Let's look at the first law, right? First law. The first law is saying that the sum of all currents entering a junction equals what? Sum of all currents leaving the junction. So which of this current is entering the junction? I1 is entering the junction. I1 started from here, right? Enter the junction D. This is our junction here. I3, the current that leaves here is I3. I3 and I2 are leaving. So that means that my I1 is entering. So I1 is equals to I2 plus what? I3. This is just like this. I have a loop here. I have my I1 here. I have what here? I3. I have what here? I2. Is that clear? This is the diagram here. This current here is still I3 because I3 is the current as entering what? I3. So I1 is entering the junction. I3 and I2 are leaving. So that means I1 is equals to what? I2 plus what? I3. This is my equation what? 1. This is my equation 1. Now the second is, now we're going to analyzing loop what? Loop A. I've already explained what loop A represents, which is our A, D, okay, A, D, C, and what? B, right? A, D, C, and B. This is my loop A. And let's analyze. Okay. For the second law, sum of all voltage must be equal to what? 0. Is that clear? Okay, so let's go. The second law, we have applied the first law, and that gave us equation 1. Let's apply the second law, all right? That says sum of all voltage in each of these loop must be equal to what? 0. Now, we have seen something like this in our previous example, right? So let's look at how we can generate that. So here, current is moving. The sign here is negative, here is positive. So across my cell, there's a rise in PD. So what will be here is plus 24 across this cell. So when we move here, the PD here is I1, R1. The PD here is what? I2, R2. But the PD here is a drop because current is flowing. The assumed current, the loop is moving from positive toward negative. But the loop across this cell is from negative to positive. That was the reason why I have to say plus 24. But across my R1, there's a drop because current must flow from higher to lower. So there will be a potential drop that is in the same direction with that of the loop. So from plus to minus. So here will give me minus I1, R1, right? So the same thing, one will keep on moving. Along this region here, there will be a drop also, which is minus what? I2, R2. Is that clear? So here we have here to be 24 minus I1 times, our R1 is what? R1 is 3 minus I2, our R2 is 4. Is 4, right? So this will give us, let's finish up here. This will give us 24 minus 3 I1 minus 4 I2. All right. This should be equal to 0. This is equal to 0 because we are saying sum of all PD must be equal to 0. So this will be equal to 0, right? So this will give us, let's move this 24 to the other side of the equation. Yeah, we're going to have 3 minus 3 I1 minus 4 I2 equals to minus 24. At the time, we can divide through by minus sign because what is common here, yes, minus. So I can say divide through by minus 1. So I will have minus 1, and what? Minus 1. This can go, right? This can go, this can go. Here becomes what here? 3 I1 plus 4 I2 equals to what here? 24. Equation 2. Now, we have generated equation 2 from the first loop. Now, let's look at the second loop, okay? Analyzing loop B. Analyzing loop what? Loop B, right? Already we know what loop B represents. Loop B represents D, E, F, and C, right? So while moving, in loop B, we don't have a battery. We only have resistors. We only have R2 and R3 in loop B. This is part of loop B. Don't forget, loop B is D, E, F, C. So along here along this branch we have R2. Here we have what? R3. So while moving, the loop direction is showing a rise because from negative to positive. Don't forget that these signs are fixed. Irrespective of your loop, the signs will not change. These signs show that the current is flowing this way. Anywhere current is flowing from will be what? Positive from the beginning. Negative. There must be a drop in PD. But your loop, if you look at your loop is showing a rise from negative to positive along this region. Then along this region, when we keep on moving, there will be a fall, right? A fall, because this loop you are seeing here is actually moving in a clockwise direction, just like we did here, right? For this other one, we have plus 24 minus I1 R1 minus I2 R2. Then in this other side here, the loop is going this way, is going up, is going up. Are you seeing it now? This is going up, but for this other one is coming down. So here we are going up. I'm not coming down. If I'm to take my loop direction this way, to not be a fall, but my loop is showing that we are going up. So for this we have positive I2 R2, right? On this side, there's a rise in PD. Then when we get to this point, there will not be a fall. Minus I3 R3 equals to what? 0. Meaning that the sum of all voltage is equals to 0. We are applying it in the second loop. I repeat again, there's a rise in PD, which is I2 R2. When we get to this point, there's a fall in PD from plus to what? Minus. So let's fix in our value. So our I2 times our R2 is 4 minus I3. R3 is 2. All must be equals to what? 0. So 4 times 2 will give us 4I2. 4I2. Here we have 4I2, right? Minus 2I3. All equals to what here? 0. I can decide to divide both sides through by 2, because what is common here and here is 2. 2 can go in all. Divide 2 by 2, divide 2 by 2, divide 2 by 2. So we're going to have here as 2I2 minus I3, right? Equals to what? 0. 0 over 2 is 0. So 2 we cancel 2. 2 here is 1. 2 in 4 is 2. So we have 2I2 minus I3 equals 0. I can decide to move this negative I3 to the other side. That will give us what here? 2I2 equals to what here? I3. This is my equation what? 3. Now let me bring out the 3 equations we actually generated. The first equation says that sum of all current entering I1 is equals to what? I2 plus what? I3. This is my equation 1. The second equation says that 3I1 plus 4I2 equals to what? 24. Equation 2. The third one is saying 2. Okay, I can just say I3 is equal to 2I2, right? I3 is equals to 2I2. I can say I3 is equals to 2I2. Okay, this is my equation 3. Please, if you are following, indicate in the comment section that you are following. If you are following, indicate that you are following in the comment section. So let's see what we have again to avoid error. So here we have I2, R2. There's a rise in PD, which is what we just did here. Here we have minus I3, R3. Here we have I2 times 4 minus I3 times 2 equals to what? 0. All right. So yeah, we have 4I2 minus 3I3 minus 2I3 equals to 0. We divided 2 by 2. That gave us what we have here. Now the next is to evaluate further. Now what we have here? Here we have that our I1 is I2 plus I3. Here we have here as our 3I1 plus 4I2 equals 24. Here we have I3 equals to what? 2I2. I can decide to substitute my value of my I3 into equation 1. It is more simpler to substitute I3. Let's put I3 and see. Put I3 equals to 2, or put equation 3 into equation 1. Equation 1 simply says that I1 equals to what? I2 plus what? I3. I want to put this into this, meaning anywhere we see I3 in equation what? 1, I will replace with what? 2I2. And that will give us what? Yeah? I1 equals to what? I2 plus, what's our I3? Is 2I3. 2I2, right? I'm replacing my I3 as what? 2I2 in equation 1. So that will give me I1 equals to what? I2 plus 2I2 is 3I2. Are we there? Now, look at this now. We have solved this. We have equation 1, equation 2, and equation 3. When we put the value of equation 3 into equation 1, that gives us equation 4. Is that clear? So here we have I1 equals to what? 3I2. Is that clear? Okay. What we notice here, I can solve this. If you look at these two equations, here we have I1, I2, I3. Here we have I1 and I2. Here we have I3 and I2. Here we have 3 unknown. Here we have 2 unknown. Here we have 2 unknown. Okay. The reason why I have to put equation 3 into equation 1 is to generate an equation that will be easy for us to solve that simultaneously. If you look at this now, after putting equation 3, which is 2I2, into equation 1, that gave us this. It gave us an equation that has 2 unknowns. And what are the 2 unknowns? I1 and 3I1, I2. Is that clear? I1 and 3I2. Then if you look at equation 2 and equation 4 have the same unknown. So I can solve equation 2 and equation 4 simultaneously. Meaning, anywhere I see I1 in equation 2, I will replace with what? 3I2. But why do we have to go through all of this? Look at these 3 equations. There's no way I can solve simultaneously. Yeah, I have 3 and 2. I have unknown 3 and 2. Yeah, I have 1 and 2. So I can't solve these 2 simultaneously. I can't solve these 2 simultaneously as well. I have 1, 2, 3. So the only way is to put I3 into I1. And that gives us what we have here as I1 equals 3I2. So I have I1 and I2, which have the same variable with equation what? 2, which are what? 3I1 and 4I2. So I will now solve equation 2 and equation 4 simultaneously. I will say solve equation what? 2 and equation 4 simultaneously. Let's see. Let's solve simultaneously. I hope you guys are following. This is one part of Kirchhoff's that's always makes the work bulky. Kirchhoff's explanation is very simple, but the calculations are quite complex and lengthy. So let's solve equation 2 and equation 4 simultaneously. Let's bring out equation 2. Equation 2 says 3I1, right, plus 4I2 equals to 24. Equation 2 is this. The new equation we generated is what? Is I1, right? I1 equals to what? 3I2. Okay, this is equation what? 4. Now, what do we do? I've already said to solve simultaneously, we have different methods. We have either by elimination method or by what? Direct or substitution method. Is that clear? So, but look at this. I can easily substitute my I1 into equation 2. So by substitution method, I will put equation what? Equation 4 into equation 2, meaning I'm putting I1 as 3I2 into equation 2. Meaning anywhere I see I1, I will replace it with 3I2. Let me repeat equation 2. That says 3I1 plus what? 4I2 equals 24. Now let's replace Here we have 3 times. What's our I1? I1 is what? 3I2 plus 4I2 equals to what here? 24. 3 times 3 will give us 9. 9I2 plus 4I2 equals to what here? 24. So 9I2 plus 4I2 will give us about 13, right? Okay, let's verify. Let's verify to avoid error. Give us about 13. 13I2. 9 plus 14 is 13I2 equals to what here? 24. Then what will be our I2? So we have 24 divided by 13 is about 1.8. So our I2 is about 1.85 ampere. About 1.85 ampere. All right. Okay, let's go through this again. Here we have 3I1 plus 4I2 equals 24. Here we have our I1 for 3I2. So we have here as, okay, 4I2. Just want to verify my equations. Equals to 24. So here 3 times 3 is 9I2. Okay. All right. Okay, let's keep on solving and see what we're going to generate at the end of the day. Please, if you are following, indicate in the comment section that you are following. If you are following, indicate in the comment section that you are following. If you are following, indicate in the comment section that you are following. Hello guys, are you guys following? If you are following, indicate in the comment section that you are following. Indicate in the comment section that you are following. Please indicate that you are following in the comment section. If you are following, indicate that you are following in the comment section. Okay, so let's proceed. Let's proceed. Please indicate that you are following. Okay, I'm just going through the figures to avoid errors. All right. Okay, so let's proceed. This, we have gotten our I2 as 1.85 ampere. The next is to find other currents, right? Other currents. From here, we can actually solve for I1. But equation 4 says what? I1 equals to what? 3I2. So I1 will give us 3 times. What's our I2? Our I2 will solve as 1.85. 1.85. So I1 is going to give us, let's multiply. Let's multiply 3 by 1.85. This is about 5.55 ampere, right? 5.55 ampere. Okay, the resistor here is meant to be 12, but we make use of 2. Please, okay, let's just go ahead. We are using 2 ohms, right? We're using 2. From the main equation itself, it's meant to be 12, but we actually make use of 2 ohms, right? So let's proceed with that same value. All right, let's proceed. I think that was what we use here. Let me verify. Okay, we used 2, I2, I3, I3, and that gave us this. Is that clear? That gave us this. So what we use here is actually 2 instead of 12, but this is still correct. So we are using 2 ohms. Please take note, as I3 is 2 ohms. So we have gotten our I1 as 5.55. Okay, to solve for I3, we have to recall We have gotten I1 as 3I2. Then I3, recall that I1 plus I2, okay, I1 rather, is equals to what? I2 plus what? I3. That means from here, our I3 is equals to I1 minus what? I2. So I3 becomes, our I1 is 5.55 minus I2 is I2 we solved as 1.85, right? So I3 becomes 5.55 minus 1.85. That will give us about 3.7 ampere. So our I3 is 3.77 ampere. Okay. Okay. I can also use this to find I3. I3 here says 2 times I2. When you multiply 2 by I2, I2 is 1.85. Let's verify 2 times 1.85. 2 times 1.85. The answer is still 3.7 amp. So this is the first aspect of Kirchhoff's I want us to take note of. All right. So let's look at another question. Please, if you are following, indicate that you are following in the comment section. Please indicate that you are following in the comment section. Okay. I would like to use the same diagram to solve using Ohm's law, simple Ohm's law, instead of solving using Kirchhoff's law. Let's see how we can apply simple Ohm's law to solve. All right. So the same diagram, let me bring it out. Sorry, I will have just maintained the diagram, the same diagram, but let's see if we're going to get the same answer. Here we have 24 volts. We have here as R1. R1 is 3 ohms. We have here as 4 ohms, which is our R2. Then we have another resistor, which is our R3, right? Okay, R3. And R3 is taken as 2 ohms, right? We make use of 2 ohms, not 12. So let's see what we're going to generate from here. Now, we can, like I said, this is a simple circuit because I have just one voltage source. So I can decide to use the normal Ohm's law. The first we need to do is to resolve these two in what? In series, by saying that R2, right? R2 and what? And R3 are in what? Are in series. Is that clear? Since they're in series, so let's find the equivalent. So the sum of this will give us what? R4. R4 will be their equivalent or their combination. Let's call their combination R4, which will give us 1 over what? R2 plus 1 over what? R3, right? Minus 1. Is that clear? This is how to resolve resistors in parallel. And that will give us what here? 1 over our R2 is 4 plus our R3 is 1 over 2 minus 1. So here we have R4 to be, okay, let's go. Our LCM between these two is actually 4. 4 into 4 is 4 into 4 is 1. 1 times 1 is 1 plus 4 into 2 is 2. 2 times 1 is 2 minus 1, right? Minus 1. So this will give us what here? 3 over 4 minus 1, which is same as 4 over 3. Is that clear? So let's verify again. LCM is 4. 4 into 4 is 1 times 1 is 1. 4 into divided by 4 divided by 2 will give us 2. 2 times 1 is 2. So 1 plus 2 is 3. All right. So when we divide that, 4 divided by 3 will give us 1.3333. 1.3333 ohms, right? So the new combination, the new cell will then be in this form. This is what we learned yesterday, right? So yeah, I will still maintain my R1 here. Then here will give us, this will give us our R4. And that R4 is 1.3333 ohms, right? Our R1 is still 3 ohms. So R1 and R4 are in series. So R1 and R4 are in what? Are in series. So let's resolve their combination. Our cell is still 24 volts. In using simple Ohm's law, we don't need to bring out the potential drop or anything. Just solve the rates like we did. If you missed my class yesterday, please go through that lectures I uploaded. I've made it public for everyone to learn. All right. So R1 and R4 are in series. So what will be our R equivalent is R1 plus what? R4. And that will give us R1 is 3. R4 is 1.3333. So my R equivalent will be 4.3333 ohms. But current is equal to V over what? R equivalent. So my V is 24 over 4.3333. So current becomes 24 divided by 4.3333. This will give us about current equals to 5.5385. If you notice, the value of the current we solve for I1 is 5.5385. Go to the lecture, you will find out that our current is corresponding, right? So that means that the current that actually emerges from this voltage is what? It's 5 points. It's 5 points. The current here is 5.5385 ampere. The current that is being delivered by the cell is 5.5385, and that current will pass through R1, also pass through R4. So R1 and R4 are sharing the same current. Don't forget. But don't forget that the combination of R2 and R3 is what gives us R4. So the total current in R4 is this. But that current will be shared among R4 and what? And R3. But the total current that flows through our R1 is actually 5 points. So for R1, my I1, which is this, don't forget the flow of current. Our I1 is 5.5, let's say 5.4, right? 5.54. So that same current, when the current gets to this, it will now split. It will split. There will be a current that will flow through here. There will be a current that will flow through here. Are you there now? So let's find. Please remember the current that passes through R2 and R3 when we use Kirchhoff's. We have already verified that current I1 is 5.5385, which is true, right? So let's find, therefore, here we have I1 is equals to 5.5385 ampere. Okay, we are trying to verify using the normal Ohm's law. So we have seen that the current that passes through R1 so is 5 point. When this current enters here, it will split. Part will enter here, and that part will enter here. So let's find the current that enters R2. To find I2, I taught us something. I gave us a formula to find the current that flows through resistors connected in parallel. If I have two resistors connected in parallel, since they are to share this current, okay, the formula says what? I2, between I2 and what? Between R2 and R3, to find I2, formula says total current times R3 over R2 plus what? R3. If I'm to find out of I2, it will be total current times R2 over what? R2 plus what? R3. Are you there? To find the current that flows through I2, I will say current, total current times resistor 3, R3 over R2 plus R3. To find that enters through I3, this is for I3. To find current that enters through R3, I'm going to use current times R2 divided by R2 plus what? R3. Let's solve for this and see what will be the results. My total current is actually 5.5385 times our R3 is 2. 2 divided by 2 plus, sorry, R2 is 4. 4 plus 2, right? 4 plus 2. So this will give us 5.5385 times, let's divide, this will give us 2 over 6, right? 2 divided by 6, multiply with, this is 0.3333, multiply with 5.5385. Our result here is about 1.85 ampere. The same currents we calculate using Kirchhoff law is the same current we got when we use the normal Ohm's law, right? The same current. That will tell you that the calculations we did under Kirchhoff's is 100% accurate. All right. So this is my I2. Now, look at this here. If the current that enters here, total current that enters here at this junction, that enter this junction is 5.54, that means there will be a split, Abi. There will be a split. So to find my I3 is simply, I will subtract 5.54 or 5.5, okay, 55385 times, sorry, minus 1.85. What I'll do, minus 5.53, okay, 5385 minus that will give me about 3.692 ampere. The same value of current for I3 we also got. All right, the same value of current. Or we can also use the formula I gave. What the formula I gave? The formula I gave for I3, we say is I times R2 over R2 plus what? R3. So my I3 becomes what? Our value of our current is 5.5385 times our R2 is 2 divided by, where we have 4 R2, yeah, R2, sorry, R2 is 4, sorry, 4 divided by 4 plus 2. All right, so let's go. We have 4 divided by, this is 4 plus 2 is 6. Okay, so we have 5.5385 times 0.6667. So here we have times 5.5385 times that will give us about, our I3 is equals to 3.669 ampere, the same value of currents. I hope this is clear. Now let's solve one more example from your textbook. One more example. Okay, let's look at another example from the textbook. All right, another example. All right, another example from the textbook. Here we have 10 ohm resistor. We have a junction here, a node rather. This is a circuit given to us from the textbook. We have our cell here. We have 6 volts. Here we have negative and positive. Here we have 12 volts. Along this region, we have our resistor, which is 16 ohms. We have a junction, point A. We have point B. We have point D. We have point C. All right. Then along this branch, we have 8 volts battery. This 8 volts. Then here we are asked to find, then the direction of current was given. You are told that the first current here, this was given to us as I1. Here we have here as I3. We have a current here called what? I2. Okay, then we're asked to find I1, I2, and I3. For this kind of diagram, we can't apply simple Ohm's law like we did. We can only apply Kirchhoff's here. All right. So what do we do first is that we have to indicate our signs. All right. Here we have a cell here. This is a negative terminal. This is a positive terminal of the cell. So here will be taken as negative. Here is what? Positive. Since current is flowing this way, this is a resistor. Let's call this R1. Let's call this what? R2. So there will be a potential drop or fall from positive to what here? Negative. Don't forget, look at this. Current is flowing downward. It means the current is flowing this way. For this is this way, right? Plus, minus. For this is downward. This was given to us downward. So here will be plus and what? And minus. So yeah, current is flowing this way, meaning here is negative, here is what? Positive. All right, this is the positive side of the cell. This is a cell, not a resistor. So here it maintains positive, here maintains one negative. Do you get the concept? But for a resistor, when current is flowing, current flows from higher voltage to lower voltage, higher voltage and lower voltage. Current flows from lower to what? To higher, lower to higher. For a cell, we are moving this way upward. So for this way, minus and plus. This side we have minus and what? And plus. All right, minus and plus. This is 6 volts, 12 volts, 16 ohms, 10 ohms, and 8 volts. I can decide to take my loop this way. I can decide to take my loop. This is my I3. Let me take it here. I3. My loop can also decide to be taken this way. So I have 2 loops. I have loop A and loop what? B. So let's apply Kirchhoff's first law. The first law says the sum of all currents entering a junction is equal to the sum of all currents. Let me shorten it. Entering the junction equals to the sum of all currents leaving the junction, right? Leaving the junction. Now the question is, which of these currents are entering and which of these currents are leaving? If you notice, I1 and I3 are moving towards junction A. This is a junction here, right? Then I2 is leaving. So sum of I1 plus I3 is equals to what? I2. So sum of I1 plus I3 is equals to what? I2. This is my first equation, equation 1. This is my first equation, equation 1. Now the next is to determine the second law. Second law says sum of all potential difference in the circuit is equal to 0. So let's analyze. Analyzing loop what? Loop A. Loop A is simply A, B, D down to A. So this is my loop A this way, right? My loop B is this. If I want to bring out all the elements in loop A, the elements in loop A, along this region, we have resistor. Along here, we have what? A cell. Along here, we also have a cell. Elements in loop B. Along here, we have a resistor. Here, we have a cell. Here, we have a cell. Okay, so let's analyze loop A. For loop A, sum of all voltage. The voltage here, I'm going this way, right? Here, we experience a voltage rise. Here, we have 6 volts or plus 6. This is plus 6 because the loop is showing it's moving from lower to higher. So here is plus 6. So along my resistor, my PD here is actually I1, R1. My PD here is actually I2, R2. Is that clear? So let's look at this together. So there's a fall in PD by minus I what? I1, R1. I'm going this way, right? Then the loop is still moving this way. Then from when we get to this cell, the loop is showing from positive to negative. Here we minus 8. Minus 8, right? Equals to what? 0. Let's finish up this. 6 minus 8 is minus 2. All right? Okay, let me finish up by saying 6 minus my I1 is unknown. Our R1 is 10. We have times 10 minus 8 equals to what? 0. So here we have 6 minus 10 I1 minus 8 equals to what? 0. 6 minus 8 is minus 2 minus 10 I1 equals to what? 0. By the time we move this I2 to the other side, that will give us minus 10 I1 equals to what? 2. Minus 10 I1 equals to what? To 2. Okay, so let's see what we are going to have at the end of the day. This will give us our I1 equals to 2 divided by minus 10, right? So I1 is simply equals to, minus 1 over 5 I1. I guess this will give us about minus 0.2 ampere. When divide 1 by 5, 1 divided by 5 is 0.2. Now look at this now. What do you notice here? The sign we have here is negative. Does not mean your answer is wrong. When you have a negative current, it does not mean your answer is wrong. It means that you're choosing direction. You're choosing your assumed direction. It's not the actual direction of the flow of current. It's not the actual direction of the flow of current. It's not. All right. That's what is negative sign here. So, but the actual value of this current is 0.2 ampere. Even if you have minus, you are still correct. If you have plus, it means plus simply means that the loop direction, okay, is in the same direction as the real current. Either. So your negative sign does not actually mean that your answer is correct. It's wrong. It simply means you are correct, but just that the direction of the conventional flow of current is not in the same direction as the current you assumed. All right, so that is what it means. Okay, that is how your textbook actually stated it. Let me read out. Okay, let me read out. The negative sign in the current indicates that the two directions of current are opposite the ones assumed. I see the same thing we are saying here. The negative sign in the current indicates that the original direction of current are opposite ones assumed, meaning that the original current that is flowing through this circuit is opposite to the assumed current. That's what this simply means. Okay, we have analyzed loop A, and that gave us 0.2 ampere. Let's analyze loop B. For loop B, analyzing Loop what? Loop B. For that of loop B, let's analyze loop B. For that of loop B, if you look at loop B, there's a voltage drop here. Loop B is still clockwise. We are assuming clockwise direction. There's a voltage drop here, right? A voltage drop from plus to what? To minus. Along this region, there's also there's a voltage rise from minus to plus. But along my resistor, there's a drop in what? In voltage. Current must move from higher to what? To lower across a resistor. So let's analyze this. The sign here would be minus 12 volts. Okay? The sign here will be plus 8 volts. But let me take off these volts since I'm just solving simultaneously. So we have minus 12, we have plus 8, right? Minus 12 along this, the loop direction shows from plus to minus, which is this. Here shows from negative to positive, which is plus 8. Then along here, we have minus I2, R2. All of this must be equals to what? Somebody? 0. All right, so let's finish up this. So we have minus 12 plus 8 is minus 4 minus I2 times R2. R2 is 16 equals to what? 0. So we have minus 4 is equal, okay, minus 16 I2 equals to 0. By that we take this to the other side, we have minus 16 I2 equals to what here? 4. So that means my I2 will be, how do we get our I2? We have to divide both sides by minus 16, right? So that will give us what here? Our I2 equals to what? 4 over minus 16. This will give us about minus 1 over 4. So I2 should be about minus 0.25 ampere. When you divide 1 by 0.25, divide 1 by 4, that 1 by 4, that's about 0.25. So this is my I2. But we stated that, don't forget what we say by this sign, right? I've already mentioned the reason why this minus sign is gotten. So our I2 is 0.25, I1 is 0.2, or we can say minus 0.2 or minus 0.25. But for the first law of Kirchhoff, we stated that I1 plus what? I3 is equals to what? Yeah, I2. We have gotten I1 and I2. Let's solve for I3. I3 will then be what? I2 minus what? I1, right? To solve for I3, I have to move my I1 to this side, becomes I2 minus I1. So that will give us what here? Our I3 equals to, our I2 is minus 0.25 minus, in bracket, our I1 is minus 0.2. So we have minus 0.2. Don't forget. So I3 becomes minus 0.25. Minus times minus will give us what? Yeah, plus 0.2. So by the time we subtract these two, minus 0.25 plus 0.2, this will give us about minus 0.05 ampere. So what do we notice here? Here we have that our I1 is minus 0.2 ampere, our I2 is minus 0.25 ampere, our I3 is minus 0.05 ampere. This is what this is the current that flows through each of the resistors. Okay, so let's finish up. Let's solve one more example. I hope you are following. Please, if you are following, indicate in the comment section that you are following. Please indicate in the comment section that you are following. Indicate in the comment section that you are following. Indicate in the comment section that you are following. All right. Indicate in the comment section that you are following. Please indicate. All right, I want us to see one more example. Then we move into something else entirely. We have a question from your textbook, both IMSU and UNN students. A question from your textbook. Here we are given a battery source. We have 12 volts battery source. Then we have a resistor here, R1, which is equals to 1 ohms. Or R1 is equals to 1 ohms. Here we have another resistor along this branch. And this resistor is R3, which is equals to 2. Here we have R3 equals to 2 ohms. Then we have a third, we have another branch here. Then we have a battery, this second battery. Okay, this battery is giving us 6 volts. Is giving us 6 volts, all right? But this resistor is R2, which is equals to 1 ohms. All right, so let's analyze this circuit. We also find the current that flows through each of the resistors. This is very simple. Okay, let me be sure that we have the accurate diagram. This R3, let me place it here. Then we have R3, which is equals to 2 ohms. Now let's solve. We just say find the current that flows through each of these resistors, meaning we have to find I1, to find I2, and I3, right? All right, guys, so let's see how we can do this. The first thing, like I always say, is that before you analyze such kind of circuits, so what do? Is to indicate your conventional sign. The conventional flow of current is always from this side of the cell, the positive terminal of the cell. This is the negative terminal of the cell, right? So the current flows in this direction. The current that enters R1 is I1. When this current gets to this point, what happens is that this current will enter this other resistor as what? As I3. Let's see, as I3. So current is flowing downward because the cell is showing the flow of current in this direction. So when it gets to this junction, let's call it junction A and junction B. When for this other side, current will flow from this region. This is plus, so this is minus, this is what? Plus. So current flows from this region. The current that flows across R2 is I2. So what we notice here, two currents are entering a junction. While one current is leaving, I1 and I2 are both entering this junction, but I3 is leaving the junction. But before we analyze this circuit, I want us to indicate our signs. Where do we experience a drop in PD and a rise in PD? So look at this now. We experience a rise here, right? Along here from minus to what? To plus as the current flows. So along this resistor, we have plus. Here is what? Minus. There must be a drop in PD, right? Since current is still flowing downward, here is plus, here is what? Minus. So along this region, there's a cell here. All right? Current flows this way across this resistor. And that will make this component of the resistor to be positive. Then we have positive and what? Negative. That means along this side, there is a drop. Current must flow from higher voltage to a lower voltage. Here we have a higher voltage, we have a lower voltage. We have a lower voltage, a higher voltage. Along this resistor, we have higher voltage and lower. Along the resistor, we have higher voltage and lower. Then I can determine my loop. Let's say if my loop is this way. If my loop is this way, I have loop A and what? Loop B. This is my assumed flow of current. I'm assuming that my flow of current is clockwise in both. I can assume clockwise, anti-clockwise. All right? Anyone you want to use the same answer. Okay, possibly, maybe let's take it clockwise and anti-clockwise this time around. Let's go this way. Let's take it clockwise and anti-clockwise this time around so that we can know how to analyze a circuit using two different directions. Okay, so the first is the Kirchhoff current law that says that the sum of all currents entering a junction is equal to the sum of all currents leaving the junction. Entering a junction, we have two currents that are entering this junction A. Then current I3 is leaving. So that means I1 plus I2 must be equal to what? I3. This is my first equation. Equation 1. I1 is entering, I2 is entering, I3 is leaving. That's my first equation. Then the second is the voltage law. That's the sum of all voltage must be equal to 0. So we're going to analyze. Analyzing loop what? Loop A. What is loop A? Let's say if this is A, let me take off this alphabet from here. Let's call here A, let's call here B, call here C, call here D. Our junction is C and D, right? Okay. We have A, B, C, D. Let's call here E and here what? F. So analyzing loop A is simply A, B, C, and D. Okay, so let's move on here. So let's go. Analyzing loop A, that will give us the sum of all voltage in loop A is 0. So if you look at this now, I'm analyzing. Don't forget, don't touch your sign. Leave your sign this way. Conventional flow of current has already told us where we experience a drop and a rise in PD across each of the resistor. That here we have plus and minus. Plus and minus. Just don't touch it. Use your loop direction to get your equation. The first equation and the second equation, right? So the first equation is this. I'm going to use my loop A to get the second equation, then use my loop B to get the third equation that will now solve simultaneously. Now let's see what will be the result of this. So moving this way, I'm moving from negative to positive. Here becomes positive 12. When we get to this, the PD across arrow 1 will be I1 arrow 1. But because I'm moving in this direction from plus to minus, that will be what? That will be minus I1 arrow 1. This is plus. I can just take it off as normal 12, right? I can still put plus 12. I'm just showing that there's a rise in PD across the cell. Across arrow 1, there's a fall in PD from plus to minus. So we have minus I1 arrow 1. Then across arrow 3, there's a fall in PD, all right, which is minus I3 arrow 3. The sum of all of this voltage must be equal to 0. All right, so let's fit in our value. Here we have 12 minus our I1 is 1. Sorry, our R1 is 1. So we have I1 times 1 minus I3 times our R3 is 2. All equals to 0. So we have here as 12 minus I1 minus I3 equals to 0. By the time we move this to the other side, this will give us minus I1 minus I3 equals to minus 12. Now, the next thing to do is that since minus sign is common among these three terms, this, and this, I can divide 2 by minus 1, by minus 1, by minus 1, by minus 1, right? And that will give us what, yeah? I1 plus I3 Alright, sorry for the interruption. I'm so sorry. But this is a live class, so my battery just went off just like that. So I needed to continue from where we stopped. I'm so sorry. So the next part is that we have been able to analyze the first loop, which is I1 plus 2 I3 equals to 12, equation 2. Let's analyzing loop 2, the second loop. And to analyze the second loop, which is this, right? We are assuming an anti-clockwise direction. Okay, we are analyzing that the sum of all voltage is equals to 0. So let's analyze and see. By the time we are moving this way, anti-clockwise, counter-clockwise, along this cell there's a rise in PD. Along this resistor 2 there's a 4. Along this there's a 4, because we are moving in anti-clockwise. If I'm to move clockwise, what we notice, there will be a rise, right? There will be a rise, and there will be what? A fall in PD here. So let's go anti-clockwise, meaning that my PD here is a rise, which is plus 6. Here will give me plus 6, or 6 rather. Then along here, our PD, this is our I2. Our PD here will be I2 R2, or negative I2 R2, because there's a fall. There's a fall from plus to minus, because the loop is showing negative voltage, right? The fall, current is flowing from higher to lower according to the loop. So we have here as minus I2 R2. Then along this region we have a fall in voltage, a fall in PD, which is also minus I3 R3 equals to a 0. Please, if you can hear me, indicate in the comment section. If you can hear me, indicate in the comment section. If you can hear me, indicate in the comment section. Please indicate if you can hear me. Please indicate if you can hear me, indicate in the comment section. Indicate in the comment section if you can hear me. Okay, so let's proceed. Now let's finish up this. So we have here as 6 minus our I2, we have I2 times our R2. R2 is given as 1 ohm, so we have times 1 minus I3 times our I3. Our I3 times R3 is giving us 2. The sum of this should be equals to what? 0, right? So let's go. Here we have 6 minus I2 times 1 is I2. I3 times 2 will give us minus 2 I3, which is equals to 0. By the time we move this 6 to the other side, becomes minus I2 minus 2 I3, all equals to minus 6, right? So what do we do here? We divide 2 by minus 1. By minus 1 by minus 1. That will give us what here? Our I2 plus 2I3 equals to what here? 6. Equals to 6. Now let's bring out all the 3 equations we have. The first equation is I1 plus I2 equals to what? I3. Equation 1. For equation 2, we have I1 plus 2I3 equals to 12, equation 2. For the third one is this, right? This is equation 3, which is I2 plus 2I3 equals to what? 6. This is the third equation. The third equation is gotten from loop 2. Loop 1, loop A, this is loop B rather. Loop A gave us the first equation, give us the second equation, which is I1 plus 2I3 equals to 12. Loop B gave us this equation that says I2 plus 2I3 equals to 6. But don't forget that the first equation says I1 plus I2 equals to what? I3. Please, if you are following, indicate. If you are following, indicate. Please indicate in the comment section if you are following. I hope my voice is clear enough. I'm so sorry that my mic is not working. It's not working for now. So please just try and increase your volume. Okay. I1 has 3 unknown. So equation 1 has 3 unknown. We have I1 plus I2 and I3. In equation 2, we have 2 unknown, which are I1 and I3. In equation 3, we have also 2 unknown, which are I2 and what? I3. Now we cannot solve this simultaneously, except we have to substitute one unknown into 2 other equations. For example, or for instance, since we are told that I1 plus I2 equals to I3, that means I3 equals to I1 plus I2. For this we have I1 and what? I3. For this we have I2 and I3. That means that I can substitute the value of my I3 as I1 plus I2 into equation 2 and equation 3. So what do? We say put equation 1 into equation 2 and equation what? 3. Meaning I'm going to substitute the value of my I3 as I1 plus I2 into equation 2. When we are done, when we put equation 1 into equation 2, that will give us the fourth equation, which is called equation 4. Then after getting equation 4, I will then substitute again my I3 as I1 plus I2 into equation 3, and that will give us the fifth equation. Now let's see. So let's put equation 1 into equation what? 2. So let's bring it and let's bring that equation 2 out. What is our equation 2? It says I1 plus 2I3 equals to what? 12. So let's put the value of our I3, meaning I will replace my I3 with I1 plus I2, because the rule says we are trying to put equation 1 into equation 1, 2 and 3. So what we do here is, anywhere we see I3, I will replace my I3 with I1 plus I2. So that will give us what here? I1 plus 2 times our I3 is I1 plus I2, all equals to what? 12. So let's expand this and see. We have I1 plus 2 times I1 is 2I1, 2 times I2 is 2I2 equals to what? 12, right? I1 and I1, these two are lightened, they can be added together. So I1 plus 2I1 give us 3I1 plus 2I2 equals to what? 12. This is the fourth equation, equation 4. Let's do the same thing for equation 3. Now what do we have here? After putting equation 1 into equation 3, we generated equation 4. So let's put the same equation 1 into equation 3. And equation 3 says what? Yeah? I2 plus 2I3 equals to 6. So anywhere we see I3, I will replace with I1 plus what? I2. That will give us what? Yeah? I2 plus 2 times our I3, okay, will give us I1 plus what? I2, all equals to 6. So that will give us I2 plus 2 times I1
is 2I1. 2 times I2 is 2I2, all equals to 6. So I2, 2I2 and I2 are like terms. They can be added together. So I2 plus 2I2 give us 3I2 plus 2I1 equals to 6. This is my equation what? 5. So when we put the value of, when we put equation 1 into equation 2, that gives us equation 4. When we put that same equation 3 into equation what? 3, that gave us equation 5. Now how do we solve for the unknowns? We have to solve equation 4. The two new equations, equation 4, I have to solve equation 4 and equation 5 simultaneously. If you look at equation 4, the unknowns are what? I1 and I2. Look at equation 5, the unknowns are what? I2 and I1, the same unknown. Okay, we obtain the same unknown in equation 4 and equation what? 5. So I will solve equation 4 and 5 simultaneously. So let's solve. Let's solve. So let's solve equation what? 4 and 5 simultaneously. Let me just bring it out. Already we know what we are doing. Let's solve 4 and 5. Let's bring out equation 4. Equation 4 says 3I1 plus 2I2 equals to 12. This is equation 4. The other one says, equation 5 says 3I2 plus 2I1. 3I2 plus 2I1 equals to 6. Equation what here? 5. Now look at the order here. The first equation here says I1 and I2. Here we started with I3 and I1. I can rearrange this to be in the same order. Alright? Meaning I can bring my 2I1 here and put my 3I2 here. So let's rearrange. Equation 5 says 3I2 plus 2I1, which is same as 2I1 plus 3I1, right? Equals to 6. Or let me arrange it here. Arranging this here, that will give us 2I1 plus what? 3I2 equals to 6. These two, they are the same thing. So this is my equation what? 5, right? This is my equation 5. So let's solve this equation 5 here. Let's solve it simultaneously. What do we notice here? To solve simultaneously, we can either use by elimination method, right? We can either use by substitution method, right, to solve. But I would prefer that of elimination method, right? But before we eliminate any terms, the coefficient of I1 and I2 must be the same, or coefficient of I2, sorry, this is I2, right? This is 3I2. Coefficient of I1 and I2 must be the same. Coefficient of I2 and I2 must be the same. Coefficient of I1 here is 3. That of I1 here is 2. So to make these two terms here to have the same coefficient, it means I'll multiply this, right? This by 2, then multiply this by 3. Let's see what will be the result here. Multiply this by 3, this by 2. 2 times 3 will give us 6I1. 2 times 2 will give us what here? 4I2 equals to 2 times 12 is what? 24. 3 times 2I1 will give us 6I1. 3 times 3 will give us what here? 6 also. Sorry, 9 rather. 3I2 times 3 will give us what here? 9I2. Then 6 times 3 will give us what here? 18. Right? Then we cannot eliminate. It means I'll subtract this from this. 6I1 minus 6I1 we cancel out, right? 4I2 minus 9I2 will give us minus 5I2. All equals to 24 minus 18. That will give us about let's check. Okay, about 6. We have 6 here. So how do we solve for I2? We divide both sides by what? By minus 5. By minus 5. So that means my I2 becomes minus 5 cancel minus 5. Our I2 will become 6 over or minus 6 rather, over 5. And that will give us about, divide 6 by 5, about minus 1.2 ampere. So the current I2 is 1.2 minus 1.2 amp. Now let's find other current. We have gotten our I2 as minus 1.2 ampere. We can either use equation 4 or equation 5 to solve for I1. Let's use equation from equation, let's say equation 4. 4 that says what, yeah? 3I1 plus what? 2I2 equals to what? 12, right? This is my equation 4, which is 3I1 plus 2I2 equals to 12. Let's use this to solve for I2. That will give me 3I1 plus, let's put this down, plus 2 times, our I2 is minus 1.2, all equals to what? 12. So we have 3I1 minus 1.2 times 2 is about 2.4, minus 2.4, okay, minus 2.4 equals to what? 12. Now, how do we solve for our I1? I'll move this to the other side. We have 3I1 equals to 12 plus 2.4, right? So 3I1, 12 plus 2.4 will give us about 14. Let me clean here. Here we have 3I1 equals to 14.4, right? 14.4. To solve for I1, we divide 2 by 3, 3 cancel 3 from here. So my I1 is equals to 14.4 divided by 3. Divided by 3 will give us about 4.8 watt amp. Now my I1 is 4.8 ampere. Now how do we solve? We have gotten I1, we have gotten I2. Let's solve for I3. To solve for I3, recall that from here, the I1 plus I2 equals to I3, meaning the sum of all current entering this junction, I1 plus I2, must be equal to the sum of all current leaving the junction. So to solve for I3, recall that I3 is equals to what? I1 plus what? I2, right? I3 equals to I1 plus I2. So my I3 becomes, what's our I1? Our I1 is 4.8 plus our I2 is minus 1.2. Minus 1.2. This will give us about, this is 4.8, not 48, 4.8. So I3 will give us 4.8 minus 1.2. The answer is 3.6 watt ampere. So that means this is our value. Therefore, my I1 is 4.8 ampere. I2 is about, our I2 is minus 1.2 ampere, while I3 is 3.6 ampere. So what do you notice here? Current I1 is positive, current I3 is positive. That means current I1 and I3 are actually moving in the original direction of the flow of current, right? Current I1 is moving. If you look at this, I1 is moving because here I have a greater voltage, here I have a lower voltage. Definitely, any current that must move this way must be bounced back by this, because this is coming at a higher voltage. Once it gets to this point, there will be a bouncing back. So the actual flow of current is meant to be this way, not even this way, because the voltage source is greater than this. So that's why our I2 is negative. Look at I2. What's our I2? Our I2 is minus 1.6 ampere. But the answers are correct. This one is just showing us that the actual direction of the flow of current is not in the direction of the assumed current of the loop. Do you get the concept here? Okay, and I've already explained why we have negative, because at this point we have a greater voltage. So this current here, the loop is in the direction of this voltage. So I1 must be positive, I3 must be positive, because it is in the direction. Are you there? Okay, but the reason why this value, this I2 is negative. If you look at this, we are assuming that the current is flowing this way, but originally I2 is flowing this way. If I'm to take my loop this way, if my loop is to be taken this way, you'll find out that the value of your I2 will be positive. Yes, it will be positive because the loop is taken this way. Because this current here, as it's coming here, it will bounce back by I what? I1. Alright? Okay, by I1. But our loop is this way. So the value of these currents are 100% what? Accurate. They're 100% accurate. Now let's move to something else.
All right, guys. So let's see if we're going to solve one more example. Please, if you are following, indicate that you are following. If you are following, indicate that you are following. If you are following, indicate that you are following. Let's solve one more example. All right, let's solve one more example. Okay, we have seen this. I think that is just all for now. All right, let's look at this question. Let me clean this so we can analyze this together. Okay. Last example, or I might likely drop this as class exercise. If I have a circuit like this, I have here. Okay, let me reduce the size. because of this board. I have a resistor. I have a cell here, a battery. The cell here is 80 volts. Here we have our 4 ohm resistor. This is 1 ohm resistor. We have a point here, a junction, and we have a junction. We have the negative and the positive terminal. Then we have here a resistor and that resistor. All right, so we equally have another loop here. Okay, so I want us to master this. This is 9 ohm resistor. This is 1 ohm resistor. And okay, we are given that here we have I3 flows through this circuit. This was given to us. Here we have 40 volts. 40 volts. I hope you understand why we call this I3, because these two, they are in series. So I mean, they will have the same currents. Okay, so that's why we call them I3. All right, so the current is moving this way. This, we have a junction A, we have another junction B. Then we are told that I2 is flowing this way. Then we are told that I1 is flowing this way at this junction. This was given to us, so this was given to us. All right, then we also find I1, I2, and I3. We have here as 8 ohms resistor. 8 ohm resistor. Sorry. Okay. Now, let's solve this question together. The first is to apply the Kirchhoff current law. That's the current that enters the junction, right? Equals current that what? That leaves the junction. If you look at this, I3 is entering this junction here, A. I1 and I2 are both leaving. So that means that I3 rather is equals to what? I1 plus what? I2. The sum of all current entering into the junction, is I3. While I1 and I2 are leaving. This is moving this way, it's moving this way. This is the first equation. The second is that we have to use the Kirchhoff second law that says sum of all voltage equals was 0. But let's assume our loop, our assumed direction. This is our assumed direction. This is our loop A. This is our loop B. Right? Okay, then let's also put our signs. This part of this cell is positive. This is negative, right? So since current is flowing this way, this current I2 enters this region and continues. So current flows this way. So here becomes, okay, this is still my plus and minus, right? The currents continue. So this side of this resistor becomes positive. This is what? Negative. Don't forget. The longest side here maintains the plus side. This is positive terminal. This is what? Negative or terminal. So as current flows upward, there will be a drop in voltage. Current flows from higher PD to lower PD. So from plus to minus. So the same current continues, right? Continue this way. Here becomes plus. Here becomes what? Minus. Along this region here, current is flowing downward. Meaning here will be plus. Here will be what? Minus. Is that clear? For this current is flowing this way. That means this will continue. It will move this way, then continue, making this side positive and this side what? Negative. I have been able to fix all my signs. With these signs, you can generate your other equations. Equation 1 is generated from the first law. So I will generate equation 2 and 3 from the second law, right? Now for loop A, let's analyze. Analyzing loop what? Loop A. The sum of all voltage. Okay. Along the cell here, there's a rise in PD. The loop direction shows from negative to positive. So here we have 80. Along this region here, there's a fall in PD. Okay, there's a resistor here. The resistor here, the current that flows through this resistor will be I2. My current here, if you look at I2, I2 is moving. The I2 continues its motion and passes through what? I1 what? Resistor. So that means that my potential drop here is what? I1, I2 times what? Times 1 ohm resistor. From the formula, V equals to IR. Meaning I'll multiply my current that flows through this resistor by that resistor itself. So here will be what? Minus, there's a drop. There's a drop in PD minus I2 times 1. Current here is I2. IR, our resistor here is 1. So I2 times 1 will give me the potential drop here. And why do we say minus? Because there's a drop in potential. Current tends to flow from higher voltage to lower voltage. Then along this region, the same thing we did. I2 will continue. Don't forget that I2, current I2 is the current moving along this pathway. It enters this branch and continues and enters this branch. So that same current is still I2, but there must be a drop in PD. And that drop in PD is minus I2 times what? Times 4. Now, along here, since my loop is this way, we are taking our loop. This component is minus, this is positive. There will be a rise in PD, and that rise in PD along the cell is plus 40. Plus 40. Then, let's keep on moving. We have two resistors here. There will be a PD fall or PD drop as this current is moving downward. So to find the PD drop, I multiply my I3 with this resistor. To find the PD drop here, I multiply my I3 with what? 9. The value of our resistor here will be plus and negative because current is flowing downward. Current tends to flow from a higher PD to a lower PD. So because our loop is clockwise, there must be a fall in PD in resistor 1 and resistor 9, right? But there's a rise in PD along the cell here. That was why we say plus 40. So let's find our loss in PD here. That will give us I3 times 1. I3 times 1 is the loss in PD. Minus, what will be the loss in PD here? Is still I3 times what? Times 9. I3 times 9. All of this must be equals to what? Somebody? 0. Wow. So let's see what we're going to generate from here. Here we have 80. I2 times 1 is minus I2. Here we have minus I2. Minus I2 times 4 is minus 4 I2. Right? So we have plus 40. Minus I3 times 1 is minus I3. Then we have here as minus I3 times 9 as minus 9I3. All of this is equals to 0. They are like terms here. So we have 80. 80 plus 40. Let me verify this sign again. Okay. Plus. Okay. That's good. So here we have 80 plus 40 is 120. Minus I2 minus 4I2 is minus 5I2. Minus I3 minus 9I3 will give us minus 10, right? Minus 10 minus 10I3. All equals to what here? 0. So let's move this 120 to the other side. That will give us minus 5I2 minus 10I3, right? Equals to what? Minus 120. I guess 5 can divide through. If 5 should divide through, this will give us, divide 5 through by 5. That will give us 5 here will give us minus I2. 5 here will give us minus 2I3 equals to 5 here will give us minus 24, right? Or I can say divide 2 by minus 5, right? Divide 2 by minus 5. So minus 5 will give us plus. Minus 10. Minus 10 divided by minus 5 will give us what here? Plus. Here will give us plus. Divide minus 120 by minus 5. What we have here is plus 24. So this will give us the second equation. Wow. Now let's see loop B. Analyzing loop B. Analyzing loop what? Loop B. Let's see what will be our equation for loop B. Loop B is this way. In loop B, we have this, and this. These are the node, right? This node, this node, this node, and this node are components of loop B. So let's go. So while moving this way, we are looking at clockwise direction, right? Where there's a rise in PD across 9 ohm resistor. There's a rise in PD across 1 ohm resistor. There's a fall in PD across our 40-volt battery. Along this region, when you keep on moving, there will also be a rise in PD across the 8 ohm resistor. So let's take it together. So the current that flows to 9 ohm is I3. There's a rise, so I will use I3 times 9. I3 times 9. Right? Okay. Along this region, our resistor is 1. But there's also a rise. But the current that flows through our 1 ohm resistor is actually I3. So we have plus I3 times 1, right? Yes. I3 times 9 for this. I3 times 1 for this. Plus because we are moving clockwise. And there's a rise, it's a rise. Okay? But along this 40 volt, we experience a fall. So minus 40 volts. When we keep on going in this clockwise, along this region, in this clockwise direction, there will be a fall, right? And so there will be a rise in PD across the 8 ohm resistor. That goes plus 8 or plus I1 times 8. The current that flows through this 8 ohm resistor is still I1. From here, are you seeing it? It's flowing through as I1. So I1 times 8 will give us the voltage across this. But because our loop direction is clockwise, and which is showing a rise in PD, so we have plus 8I times 8, all equals to what here? 0. 9 times I3. 9 times I3 will give us 9I3. I3 times 1 will give us I3 minus 40, right? Minus 40 plus 8I1, all equals to what? 0. So I think we have like terms here. 9I3 and I3 are like terms. They can be added together, and that will give us what here? 10I3. Okay, 10I3. All right. Plus 8I1. When we move this to the other side, becomes equals to what here? Plus 40. So I think 8 can divide through. 40 divided by 8 give us 5. So I can divide 2 by what? Okay, by 8. No, by 2 rather. By 2. Let's divide 2 by 2. By 2. By 2. 8 cannot divide 2. So it's 2. 2 is a common factor there that can divide. So yeah, that will give us 5i3 plus 4i1 equals to what? 20. This is equation what? 3. So the next thing we need to do is to solve equation 1, 2, and 3 simultaneously. So let me bring them out here. Let me bring them out. Okay. I think I have to remove this diagram. The major thing is that I've been able to generate the equations I need. So let me just take off this diagram so I can have more space. Okay, so let's go. The first equation we have says that I3, right? Or I3 equals to, the first one says I3 equals to I1 plus I2, right? Equation 1. Don't forget. The second equation says that I2, okay? Okay, let me say the first one says I1 plus I2 is equals to what? I3, right? This is the first equation. The second one says I2 plus 2I3 equals to 24, equation 2. The third equation says 5I3 plus 4I1 equals to 20, equation 3. So what do we do here? What do we do here is to solve simultaneously. So the first thing we need to do is that already we are told that I3 is equals to I1 plus I2. So I can simply put I3 as I1 plus I2 in equation 2 and 3. So I will just say put equation 1 into equation what? 2 and what? Equation 3. For equation 2, equation 2 says I2 plus 2I3 equals to 24. So let's replace I3 as this into equation what? 2. So that will give us our I2 plus 2. Our I3 is I1 plus I2. 2 times I1 plus I2 equals to 24, right? 24. Okay, let me verify this. Okay, all right, we are in the right track. Sorry, I need to verify if this is the actual equation we got in the diagram, because I cleaned the diagram, so that made me be a little bit confused, but I've clarified myself, so we can solve for that now. So I2 becomes what? I2 plus 2 times I1 is 2I1, 2 times I2 is 2I2 equals to 24. So let's add up this and this are like terms. That will give us I2 plus 2I2 will give us 3I2 plus 2I1, all equals to 24, right? So this will give us equation what? Equation 4. So I'm going to do the same thing. Let's put equation 1 into equation 3. For equation 3 says 5I3 plus 4I1 equals to 20. So let's put equation 1 into equation 3, meaning I will replace my I3 with I1 plus I2. So here we have 5 times I1 plus what? I2 plus 4I1 equals to what? 20. So let's finish up this. So this will give us 5 times I1, give us 5 I1 plus 5 I2. I will expand this. 5 times I1 is 5 I1. 5 times I2 is 5 I2 plus 4 I1 plus 4 I1, okay, plus 4 I1 all equals to 20. So these two are like terms. 5 I1 plus 4 I1 will give us 9 I1 plus 5 I2 all equals to 20. Okay, this is equation. This is equation 4, right? This is equation 4. This is equation 5. This is equation 5. Okay, so what do? We have to solve equation 4 and equation 5 simultaneously. Okay, let's solve simultaneously. Equation 4 says 3I2 plus 2I1 equals to 24. Equation 5 says 5I2. This is 5I2 plus 9I1 equals to 20. Don't forget. So this we have here as equation 4. This is our equation 5. Okay. Equation 4 is this. Equation 5 is this. 9I1 plus 5I2. I have to interchange their position because I want to solve simultaneously. So what do we do here? We multiply this by 5, right? Multiply this by 3. So let's see what we're going to generate from there. While we're multiplying this by 5, so the first term can be the same. Coefficient of the first of this of I2 must be the same for we to eliminate, or coefficient of I1 must be the same. So I can just say multiply this by 9, this by what? By 2. But let's work with this first term, right? So 5 times 3 will give us what here? We have 15 I2. 5 times 2 will give us what here? 10 I1 equals to 5 times 24. 24 times 5 is 120. This is 120. For this other one, 5 times 3 is equals to 15 I2. Okay. 9 times 3, they will give us 27. 27 I1 all equals to 3 times 20, give us 60. Then we cannot eliminate, right? 15 I2 minus 15 I2 will cancel out. 10 I1 minus 27 I1 will give us about minus 17. So 10 minus 27, this is 27. Sorry, this is 27 I1, right? This 27 I1. So 10 I1 minus 27 I1 will give us minus 17 I1 equals to 120 minus 60 will give us 60. So what do we do to solve for I1? Divide both sides by minus 17 by minus 17. So this can go with this. That implies that our I1 is 60 divided by minus 17. This will give us about our I1 is equals to minus 3.5294 ampere. 3.5294 ampere or 3.53 ampere. All right. Now the next is to solve for our I2. Let's solve for I2. We can actually solve for I2 using either equation 3, equation 4 or 5, right? Either equation 4 or 5, all right? Either equation 4 or 5. Our equation 4 is saying this. Equation 5 is, let's use equation 4. Here we have 3I2 from equation 4. Equation 4 says 3I2 plus 2I1 is equals to 24, right? 24. So let's solve. That will give us, already we have gotten our I1 as minus 3.5294. So here will give us what here? 3. Okay, we have 3I2 plus 2 times minus 3.5294. Let me take off this. This space is too small. Here we have 3I2 plus 2 times. Our I1 is minus 3.5294 equals to 24, right? All we just did there was to substitute the value of my I1 as this, because I1 is gotten as this. So multiply 2 by 3.5294. This by 2. This will give us our 3I2 to be 3I2 plus 2 times this value will give us minus 7.0588, all equals to 24. So what do we do to solve for this? To solve for I2, that will give us 3I2 equals to 24 plus 7.0588, right? So I'll move this minus 7.0588 to the other side. It will add up with 24. So that will give us plus 24. Here we have 31. So 3I2 equals to 31.0588, right? So here we have here, our I2 becomes 31.0588 divided by 3. To solve for I2, I have to divide both sides by 3. So let's divide the value by 3. Our I2 is equals to 10.35 ampere. So I've gotten my I2 as 10.35 ampere. The rest is to solve for. Let's solve for I3. To solve for I3 is very simple. To solve for I3 is very simple. So we can easily solve for I3, yeah? To solve for I3, you just have to say, recall that I3 equals to what? I1 plus what? I2. So I3 will give us, our I1 is minus 3.5294 plus our I2 is about 10.35, right? 10.3529. The value here is 10.3529. That's our value of I2. So let's add up this. So this value plus this will give us 3.5294. Our I3 is equal to 6.8235 ampere. Therefore, our I1 for this question is minus 3.53 ampere. Our I2 is 10.35 ampere. Our I3 is 6.82 ampere. Final answer for this question. All right, guys, so let's proceed. You're welcome. You're welcome. You're welcome. All right, for those of you who just join us, you're welcome. Okay, Raj Singh, you are welcome from India. Thank you for joining us. This is Kirchhoff's law. All right. So please make sure you follow up. Make sure you follow up. We have already done the first session. That was yesterday. And we talked about DC current yesterday extensively. Please make sure you go through the videos. All right. So this is the last question we have for now. Let me go through the past questions to see if there are other questions for us to analyze. Please, you are free. Our WhatsApp number is this. This is our WhatsApp number. If you want to join our WhatsApp group, this is our WhatsApp number. Or if you need a private class, you can WhatsApp me. A private class on any course in physics, you can WhatsApp me on this number. Then I'm going to be your personal coach. Personal coach, all right? Direct coach on any course in physics, all right? You can WhatsApp me on this number if you need a personal coach. Let me drop some assignments if at all there is. But let me go to. Okay, this is an assignment for every one of you. Assignment for every one of you. Here we are giving a battery. We have a 10 volts battery. We have 4 ohm resistor. We have another resistor here. We have this is 6 ohm. This is 10 volts. This is 8 ohm resistor. Okay, let's call this R1. Let's call this out. This is R3. This is our R2. So what we notice here, let me just show us the direction of current. Current will flow through here. I1 is here, right? There's a current that flows through here. This is mine. Here we have what? Here we have I3. That means there will be the other current will be what? Here will be I2. I2 will flow through our auto resistor, right? Then we are also find I1, I2, I3 using Kirchhoff's law. Find I1, I2, and I3. Okay, the voltage source, the voltage of this battery is 4 volts. The voltage is 4. R3 is 6, R2 is 8, R1 is 4. The voltage here is 10 volts. So please drop your answer in the comment section. Drop your answer in the comment section, please. Drop your answer in the comment section. Ensure you subscribe, share the link to your friends in every platform. Let them have access to this full lecture, full detailed lecture. So in my next class, we'll be talking about instruments using DC. We have DC and instruments, right? And instruments, we shall be looking at the instrument aspects of DC. We'll talk about the meter bridge, the potentiometer. We'll talk about the multiplier, the shunt resistors, and so on. We'll be discussing under instruments. That will be tomorrow or next. But I will announce the class. Just make sure you subscribe. Once you subscribe, Whenever we're having a class, you will receive a notification from YouTube. All right. So please make sure you subscribe and click on the bell for more notifications. Thank you so much, guys. So please, this is your assignment. You can determine your loop. You can determine your loop either clockwise or anti-clockwise. Anyhow you want to take your loop. So let me not indicate your loop. Let me not assume a loop for you. Just assume your loop and tell me the value of your I1, I2, and I3. God bless you, everyone. Thank you for joining this class. I really appreciate it. See you in my next class. Thank you.